Good afternoon. I'm Dilen Hettiarachchi, and welcome to today's webinar titled Inside the Blackbox, the Science Behind the Magic of GenAI. This session will unravel how generative AI models like large language models and image generators are built and why they are transforming industries worldwide. Guiding us through this fascinating topic is Dr. Sadeep Jayasumana, Chief Scientist at OCTAVE. Before joining OCTAVE, Sadeep was a staff research scientist at Google Research in New York, where he worked on core areas of generative AI, including large language models, image generation, and transform architectures. His industry experience also includes roles as a machine learning research scientist in self-driving car technology and algorithmic trading. In academia, Sadeep earned his PhD in computer vision from the Australian National University, followed by a postdoctoral position at the University of Oxford, where his research focused on deep learning for scene understanding. With a unique blend of theoretical expertise and hands-on experience across academia and industry, Sadeep is well equipped to walk us through how generative AI works. Before we get started, I'd like to let everyone know that we'll have a Q&A session at the end of the presentation. If you have any questions as we go along, please feel free to add them in the chat at any time. We'll collect your questions and address as many as we can during the Q&A. With that, I'll hand things over to Sadeep to take us inside the black box of GenAI. Sadeep?
Thanks, Dylan. Let me share my presentation.
Sure.
Can you see my screen okay?
Yeah, it's visible, sorry.
Right.
You can go ahead.
Right. I guess my video is on as well. Can you see me as well?
Yes, we can see you.
Okay, cool. Welcome, everyone. I'm Sadeep, and today I'm going to talk about Inside the Black Box, the science behind the magic of GenAI. And so this presentation is going to have three main parts. In the first part, I'm going to talk about what GenAI is and how it works. And secondly, I'm going to talk briefly about GenAI applications. And thirdly, there were some requests to talk about how to get into this field of AI and GenAI. So I'm going to touch briefly on that as well. But mainly, the most of the content will be on the first section of the presentation, how GenAI works. So let's get started. And this is quite a technical topic, but I'll try to get into that without using too many formulas or equations. So that said, this is going to be my first slide of the presentation. So maybe this has a little bit too many equations. So let's come back to that later and start with a slide which has fewer formulas. This one. Sounds about right. Okay, so GenAI, it's a machine learning model, and generally a machine learning model, like as any function that you would write in a computer program, it has inputs and outputs. Based on the type of input and output, machine learning models are broadly categorized into two categories, discriminative models and secondly, generative models. So our topic is going to be on generative model, the second type of model. But discriminative models have been around for a long time in machine learning as well. So let's try to understand the difference between these two models. So here's a discriminative model. So it takes an image as input and it tries to identify the profession of the person. So here you have Shah Rukh Khan and we have a deep neural network try to identify the profession of the person, and then it correctly identifies that it's an actor, as you can see here. As you can see over here. So that means we are trying to model the probability of the label. So that's the profession. So one of the three labels given the image. So this is the conditional probability notation. I hope you're familiar with that given notation. So probability of the label given image. So that's why it's called discriminative. You try to discriminate the image based on like its content into different labels. And sometimes these labels can be like, instead of giving a single label, you might have to give like a probability distribution. So here in this case, maybe it's very clear that they are an actor. But if you have someone like this, a Sri Lankan politician, like then you have the question, are they a politician or are they an actor or is that a thief? So that could be a little bit ambiguous. So in that sort of scenario, maybe instead of just predicting a single label, we want to predict a probability distribution over labels, as shown here. So it's a discrete probability distribution. We have three labels here, and then what I'm predicting is a probability distribution. Hopefully, they are a politician most of the time, and an actor sometimes, but hopefully not a thief, or a very little probability that they are a thief. So that sort of model, that sort of output we can get, but still we are modeling the label given the image, and this is a low dimensional problem. So if you look at your output space, these just three outputs, right? Only three labels, and then you are modeling a probability distribution over those three labels. So in real world, these three labels can go up to maybe 1,000 labels in ImageNet, for example, but still it's a small number of uh, labels, or it's a reduced dimensionality, like a small, like it's not that high dimensional. Even 1,000 is not that high in discriminative modeling. So this is kind of easy, and people have been doing this for a long time because this doesn't require a lot of compute. You can even do it on a mobile phone, or like your Apple Watch, or whatever. The second kind of model is the generative model. So remember, like again, we are modeling the label given the image. In generative model, you sort of flip these two. So now we are talking about probability of the image given the label. So now the input to the neural network is the label, actor, or whatever the description of the image you want to generate. And then in the output, you expect an image. Now, this becomes a much harder problem because of the dimensionality. So we know that the modern high resolution images, they are very high dimensional. They are very high dimensional, maybe 1024 and 1024 resolution. So that means there are million pixels. And also, essentially, like we are interested in RGB images more often. So that adds another 3 dimensions. So that means we are talking about a 3 million search space. So that is much higher than what we saw previously, which was just 3 or 1,000 at most. But here now we are talking about 3 million. So that changes everything, because now it's a very difficult problem to model a probability distribution over this sort of like a very high dimensional space. So the actor and that the image generation, for example, you might generate an image like this. So I fed actor into an AI, and accidentally it generated an image that resembles a younger version of my father for some reason. That's completely coincidental, but these are the sort of images that we can generate with these generative models. Again, this is a high resolution image, so that means this is a very hard problem. But so that's why generative models were not that popular like past few years, like maybe like 5 years ago. But in the recent years, people have picked up in terms of like technology, the GPU power, the electricity available to train these models. Because of all these advances, now generative models have become feasible, although it's a very difficult problem. Right. Okay. So now that you understand the difference between generative and discriminative models, let's try to understand how generative models work. So here I have another typical application of a generative model, language. So what we had previously was image generation, but this is language generation, similar to LLMs that you use, ChatGPT, Google Gemini, Anthropic Cloud, or whatever. So they are the main problem that they solve is that they complete sentences, or they complete text. For example, I might feed I accidentally sat on, and then your model is supposed to generate the next word. And then after it has generated the next word, then it will generate the word after that, and then the word after that. So that's how these generative models actually work. So that ChatGPT, for example, has a like nice visualization. Like it looks like someone is typing, or someone is generating the text, the output you get at ChatGPT. So it's a visual effect, but that's actually how the model works as well. It works word by word. So every time it generates a word, it runs the model, and then it feeds that generated word into the model in the next iteration, and then generates the next word, and then feeds those two words and generate the next one, and so on. So if you want to predict n words, if you want to generate n words here in the output, so that means you have to run the model n times. So that's why these models are a bit slow as well, because they're quite expensive to run. But anyway, so let's forget about that part. Let's assume that we are only interested in producing 1 word. So we have this sentence. Uh, I accidentally sat on a, and then we are interested in producing just one word to complete this sentence. So how would we go about this? Now, this is done through what known as a transformer neural network. So the idea is we have a neural network. This is the black box that I'm going to open up in a bit. But for now, we are feeding our sentence into this black box. I accidentally sat on a, so that's what I'm going to feed. And then this black box is supposed to understand the sentence and then complete the rest of the sentence. For example, because the word accidentally, it will understand that this is a it's supposed to be like a funny word or something. Because if you say accidentally sat on a chair, then that's not that interesting, because it's not an accident. You sit on chairs all the time. So maybe cake is more appropriate or more suitable in this context. So transformer network has to understand all that to produce the correct next word. So mountain maybe, for example, doesn't make any sense. Horse maybe, but it's not something you would accidentally sit on. A chair, again, not an accident. So cake is maybe the most appropriate word. But to make that decision, transformer network has to understand, like really understand what this sentence is about. It has to understand this verb, sitting, and then it has to understand this adverb, accidentally sitting, and it has to understand like who is sitting on whatever the thing, and yeah, this part and all that. So that's the challenge that this transformer network has. Right. So now let's try to open up this black box a little by little. But before doing that, we want to understand an important mechanism that is going inside this transformer network, which is known as the self-attention mechanism. This was published in a paper by Google in 2017 called "Attention is All You Need." And so in that paper, people propose this mechanism that helps this sort of understanding that I mentioned earlier. Okay, so now let's try to understand how that mechanism works. So again, like another analogy for this would be like your brain, right? So we are trying to create a version of your brain. So that's the black box. And so that brain is supposed to understand everything and produce the next word. But again, this is a brain on a computer. That's why we call it artificial neural network, to be more precise. So it's like mimicking your brain on a computer. Okay, so now we are trying to understand the attention mechanism. So first of all, now this is our sentence, right? I accidentally sat on a, okay, so that's my input and I'm interested in predicting the next word. Now, before doing anything, we have to convert these things into numbers, because computers like, GPUs and all these mathematical things, they are not really good at working with words directly, but they're really, really good at working with numbers. So GPUs are, for example, very efficient in multiplying numbers and multiplying matrices and that sort of thing. So that's what we are going to do. But to do that, first we have to convert each of these words into numbers. And to do that, we use something called the dictionary. So what we do is let's say we work in a restricted setting, just for the purpose of explanation. Let's say we work with only English language, and let's say we work with all the words in the English language. I don't know how many words are there in the English language. Maybe as a ballpark, maybe let's say there are 100K words in the English language, and I have organized them alphabetically here, starting from apple or whatever, ending with zoo. These are all the words in the English language. And for each word, I store a vector. So this is like a bunch of numbers, right? So nothing fancy, just a bunch of numbers with some length. So let's say this is like 1 to 8 or something. So that's the length of the vector. But inside that vector, we just have numbers, random numbers to begin with. So it can be like 0.5, 0.8, 0.2, whatever. And then for each word, we have such a vector. So if we have 10K words in our dictionary or the vocabulary, we'll have 10K such vectors. So in machine learning, this is actually called a dictionary because, it is a dictionary collection of words. But instead of meaning, we have a vector for each word, right? And also more technically, it's sometimes called an embedding table. The idea is again the same. You just have a word mapped to a vector. So every word is mapped to a vector in this dictionary, right? So there will be 10K words. Okay, so we have that. And then what we first do is we go and look up in this dictionary what's the what's the vector corresponding to this word I. So it will be there somewhere between C and S. There will be like word I, and there will be a vector corresponding to that. And then we just bring that vector over here. And then accidentally again, similarly, we look up in this dictionary. So it's very similar, you look through a dictionary, like, I don't know, Malalasekara dictionary or whatever, and then you try to find the meaning of that word. But instead of meaning, you find vectors here. You go to this dictionary, it's actually called the lookup. So if you work with TensorFlow or something, this step is called lookup step, because that's what it is. You just look up in the dictionary and collect the vectors. And yes, so that's how you convert your words into vectors. Now, if you look at this now, as I was saying earlier, these vectors, they have a fixed length. So in my case, this is 1 to 8. So we can just call it K, 1 to 8 dimensional vectors. And then you have the sequence length, which is just the number of words or the length of your sequence. So in this case, it's just 1, 2, 3, 4, 5. There will be 5 words. So there will be 5 vectors. Okay. So now this thing is actually like you can write it down as an array, which is just like k vectors, sorry, 5 vectors, and each vector has k elements. So it's 5 comma k tensor or an array. So in deep learning, we use the term tensor because we don't want to restrict ourselves into just 1 dimension or 2 dimensions or whatever. So tensor is usually like another name for a multidimensional array. If you are familiar with more traditional computer languages, we have multidimensional array. So a tensor is a multidimensional array. So now you can store this thing as a tensor because it's just a 5 by k vector or a multidimensional array. Okay, so now we have that. Now we want to have some interaction between these vectors. So we want to understand, for example, we want to understand that this verb sat is associated with this adverb accidentally, and it's associated with this subject I, and so on. So how do we create that interaction between these vectors so that they can deeply communicate with each other and understand the full meaning of this whole thing, or of this sentence as a whole? So that's the attention mechanism that we are going to talk about. So let me give you a simple analogy. So these vectors are now like people, right? Now I have 5 vectors. So I have 5 people here. And then this is like a speed dating scenario. These people, let's say these people are interested in dating each other. And so we put them in a room. We organize an event and put them in a room and then ask them to talk to each other and get to know each other so that they can communicate very well and get to understand each other. And for each person, I asked them to, like, so this is a person, for example, who is going to participate in our speed dating scenario. They are going to hold 3 boards. In one board, they are going to say what they are looking for. Let's say like this lady over here, she says that I'm looking for a dog lover. So that's what who she's interested in dating, right? Query. And then, so that's what she's looking for. And then she's going to hold another board, which is called the key. That's what she's advertising, right? That's what she claims to be. So for example, this lady is saying that I'm an angel, right? So I'm the perfect person for you. So that's the second board they are holding. And the third board they are holding is the actual thing they are bringing in. For example, there are some people who advertise themselves as the perfect partner, but when you spend some time with them, you understand that they're actually quite the evil person. So that's the actual content you get from that person, right? Uh, there can be scenarios, in the university, you start some relationship with someone. They say that they're an angel, but it takes 4 years for you to understand that they're not what they claim to be. And then by that time, you are too late. So yeah, so that sort of a scenario can be there. The key and value can be different, and query is what they are looking for. Okay, so now with this in mind, let's look at all the vectors. So we have 5 vectors corresponding to the 5 words in my sentence or partial sentence. I accidentally sat on a, and then I have 5 vectors. So vectors, as I was saying, like these people, and then they are holding boards, and then now they talk to each other. They exchange like their key and their queries. They go with their query and then they try to see whether their query match with other people's keys. So technically it's like it's an inner product. So query is what you are looking for, right? And then key is what the other person is advertising. So so your relationship is based on like the alignment between what you are looking for and what the other person is advertising. So and in mathematically, like you measure the alignment with an inner product. So if you have two vectors in a vector space, you use this inner product to measure how closely aligned they are, right? Because if they're close to each other, your inner product will be higher, given that the vectors are normalized. So that's sort of like a weight. So this is once you take the inner product, this will be a weight. This term will be a weight. So it can be high or it can be low. And then the value is another vector. So the idea is the value you are getting from the other person, it's weighted by this weight, like your alignment between what you are looking for and what they are advertising. So this mechanism is like a very oversimplified version of that, but this mechanism is called the self-attention mechanism. So the idea is it's a very rich interaction because now so I've here shown only one interaction between this lady and other people. So she takes her query. So this is a query, and then she interacts that query, takes the inner product between that query and the keys of other people, right? So if there are n vectors here, right? There are n vectors here. N is equal to 5 in this case. So this lady now has n connections. Like she might have a connection to herself as well. So if you see this 1, 2, 3, 4, 5. So she has n connections. This lady. But similarly, other people will also do the same thing. So this guy over here, he will also go and interact or take inner product between his query and other people's keys, right? And this person will also do the same. This person will also do the same. So actually, there are n times n connections here, right? N time n connections here. So this is quite an important point. So this is why transformer networks are expensive, because if you actually think about it, it's actually order of n squared interactions. So it's very rich because you're connecting like every which way. But it's also very expensive in terms of compute. So that's why NVIDIA is making all the money. To do this thing efficiently, you need efficient hardware like GPUs. And everybody wants to do like grow the scale and train this with more data and all that. And because of that, you need more and more compute. So that's why these NVIDIA GPUs are in high demand. So for example, if you can come up with a much better algorithm with the same richness, then maybe like you can end up winning the next Nobel Prize, for example. All right, so that's the attention mechanism, but doing this interaction once is not good enough. We just have to do that several times. So that's just layering. So you do the same thing, the exact same thing, but you do it multiple times so that people can like really communicate and get to know each other. So that's what you hear as like layers in a transformer neural network. So it's just this self-attention stacked on top of each other. So in a real neural network, transformer neural network, you will have many of these self-attention layers. So in the latest transformer network, it could be like hundreds or even thousands of layers um, of self-attention. So if you look at the thing, like it will be very complicated. Like here, I have drawn only some connections because remember, as I was saying earlier, at each layer you have n squared connections, right? And then in this layer you have another n squared connection, and in this one you will have another n squared. And if you have L layers, then the total complexity will be L times n squared. So these are very big numbers, right? It can end up being like millions or billions of connections, even getting closer to trillions these days. Okay. So it would be like similar to your brain now, because there are so many connections. There are so many neurons. So neurons are like, these elements in your vectors. And then the connections are the, communications that I was talking about earlier. So it's like now getting a bit closer to your human brain with, billions of connections and billions of weight. Okay. Now, then the problem is, how do you make this thing learn the language or image generation or whatever it is you're interested in? So that's the real challenge. How do you make this thing learn? Now it's kind of similar to turning knobs for your brain when like in artificial neural network, right? So I've drawn a brain here, but actually this is implemented on a computer. And your artificial neural network that you implement inside the computer will have multiple knobs, like these knobs shown here, and then you can turn them to get the required output, right? You can turn, like you can change. So just like a DJ would optimize for the output, you can turn these knobs and get the output you require. But the thing is, you can't do this manually because, as I was saying earlier, you have billions of connections, billions of knobs. So, and it's very difficult to understand, like if you turn this knob over here, how that will affect the other knob over there, right? Because there are billions of them. It's very difficult to manually decide that. So we need that automated algorithm to automatically turn these knobs until we get the required output. So we are now going to look at that algorithm. How do we do that turning the knobs? Or like in machine learning, we call it training the algorithm. So we have the brain, the primitive brain, which doesn't understand anything. Now we are going to train it. So that's what we are going to look at next. Okay, now how do we train it? First of all, we need an objective. For example, the objective for this DJ would be like, maximizing the entertainment of the audience. So, and they get the feedback from the audience all the time. Like when they turn knobs, like if the audience is like boo or something, then they know that they are doing something wrong. On the other hand, if the audience cheers, then she knows that she's doing something right, so that she can do the optimization. So we need a similar kind of mechanism here. We need some kind of an objective, and we need a signal to know that we are doing well. So that's what we are looking for here. So that's sometimes called the training objective. So what we do is we first go on and collect some sentences on the internet. So I'm back to the previous example that we were discussing. We are on the task of completing a sentence. I accidentally sat on that's the part of the sentence, and it's up to me, or it's up to the neural network to complete that sentence. So how are we going to complete that sentence? That's the challenge. So the first thing I'm going to do is I'm going to go to Wikipedia and books and New York Times articles and everywhere on the internet. I'm going to find some true sentences where people have written down proper sentences. So this is where these companies like OpenAI got into the trouble because they use some copyrighted materials as well, like some authors' books and New York Times articles, like articles written by journalists. Like they have spent their time and effort doing those things, and then OpenAI just stole all these things on the internet. So you can get into trouble. But let's just keep things innocent, and let's say we just use Wikipedia articles where people have donated their times and written full sentences. So your sentence that you extracted from Wikipedia, it says, "I accidentally sat on a cake," right? So this is the true sentence that you got from Wikipedia. But now you have the model, and into the model you feed this part of the sentence. So this would be your input to the model. So this is the input. We'll just call it X input, and the output the model produced is chair, right? So this is the model output, current model output. And now we have a problem because model says something, but the actual ground truth. So this is like the golden truth, right? When you are training, because it was written by a human. So humans are our gold standard at this stage of training. So we want this model output to be closer to the actual thing we saw on the Wikipedia, the actual thing written by a human. To do that, again, we have to quantify these things. So we are going to look at the discrepancy between these two words, the predicted word and the actual word, right? We are going to measure the distance between these two words. So that's what I have here. We are going to measure the discrepancy between the model output, which is cha, and the ground truth, the actual output, which is cake. And yeah, so you can formulate it as a distance. And I'm not going to go into like too much of mathematics, but in machine learning world, there's a distance called the cross entropy distance, or categorical cross entropy distance, where you can really quantify this. So you can end up with a number like a tangible number like 0.5 or 0.8 or whatever to measure the distance between these two words. So that gives you a measurement of like how off you are from the human's writing. So, like example, let's say if your distance is very high, like 10,000 or something, then you know that your model is doing quite badly. But if the distance is very low, like 0.1 or something, then you know that your model is doing well, right? So that's why we call it loss. Sometimes it's called the energy as well, but in modern machine learning or deep learning, it's more common to call it the loss. And we are interested in minimizing the loss, right? So lower the loss is the better. Okay, so now we have this loss, and then now let's talk about how to minimize this loss. So that's our objective. So that's like the the audience feedback that the DJ gets. Now we are going to optimize for that, optimize for the entertainment of the audience. We are going to optimize the loss. We are going to minimize the loss. And if you look at this function now, cross-sectional function, the last function, you see that so the T is the ground truth, which is just this one, right? Cake. I have it as T here because it's the target, T for target or the ground truth. So that's T, and FWX is the model output. So that's jar. That's this one. Okay, and X is the input. So that was this one, what you fed into the model. FW is the model, right? FW is the model. And a W here, which I have highlighted in red, it represents the knobs, these knobs. So it is just, I just wrote it as W, but in practice, this W is not a single number. It's actually like it represents all the parameters. So you can think of it as a vector collection of all the parameters, right? So it can be like a vector that has a length of 1 billion or something, or 100 billion even. Okay. But for simplicity, let's just assume that it's a single number. It's much easier to discuss when we have real numbers. Okay. So W. So this is the knob, right? And as I was saying, for simplicity, we are going to assume that we have only one knob to turn. Right? This is the knob we are going to turn. So now the question is, how do we turn this knob to minimize this loss? Right? Okay. So it's sort of like this. This is the loss function. The loss function over here. That's the y axis here, and W is the knob that I'm going to turn. So it's just a real number, a single number. And so if you look at the loss function, it could be something like this, right? And then maybe we'll start the knob at a random position, and then so W0, that's the initial position. And if you look at the loss at that point, so maybe it's a high number, right? So let's say it's like 100. But now you want to optimize it. You want to come to this minimum. That's the minimum you can get for the loss. Let's say this is like 1, right? So you want to somehow move towards this, starting from W0, you want to move towards this optimal W. But you don't want to move this way, right? Because if you are moving that way, then you are in trouble because you are now increasing the loss. So maybe it will become 200, right? So you are increasing the loss. That means you are getting further and further away from the human ground truth. So that's not something you want. You want to be as close as possible to the human output. So you don't want to go here. You want to go here towards the optimal, right? So how do we do that? So let me give you another analogy. But think about it. You want to go towards this bottom, right? The bottom of the curve. So it's like this. Okay, so now I have it in 2 dimensions. So this is the bottom of the thing. So instead of 1 dimensions, I have 2 dimensions now. So this is like the curve we were saying earlier, right? And then we are trying to go to the bottom of that curve, right? And then this is the person, right? Like this is you. So you started here, and then you are trying to go to the bottom of this valley. So what would you do? Try to think about it, right? Let's say you are blindfolded, you can't see anything, and you are in this valley, and then you want to go towards the bottom, but you don't know where it is. What would you do with your eyes closed? Any suggestions? So, so one thing you could do is while you have your eyes closed, maybe you can use your feet to explore locally. So you just see locally where the descending direction is, because you know you want to go towards the bottom, right? So you use your feet to explore the flow around you locally, right? Locally, just explore the flow around you, and then you move towards the steepest descent, this direction, right? Only one step. You take a step, and then after that, you do the same kind of exploration from there. Again, you are going to explore locally and then take a step towards the steeper descent. So that might work at some points, but some point you will move towards like somewhere else, right? But then on average, it actually works. So sooner or later, if you keep doing this, like exploring locally and taking a step towards the slope, steeper slope, then you will end up in the bottom. Okay, it's not a very good answer because you have water. You don't want to end up in the water, but you know what I'm talking about, right? So on average, if you keep doing this, you will end up in where you want to be. So this is another analogy. So it's like a bowl, right? So this is like a bowl, and this is like a marble. So let's say you have like you ate porridge in your bowl, and then you forget to wash it, and now you have like a sticky bowl, and you have a marble in your sticky bowl, and then you want to put this marble into the bottom. So what can you do? You can just uh, give it a small nudge so that it will move towards the bottom, and then you keep on hitting it, and then at the end it will reach the bottom. Right? So that algorithm is called the gradient descent algorithm. So this is like this mathematical explanation. Just let me explain it. So this is exactly what I described earlier. So let me, yes. So yes. So W is your current location. So that's your current location, this one. And W next is your next location. So this is your next location. And so what this means is that to get to the location, next location, what you do is you take the derivative of your loss function. So this E is the loss function. So as I was saying earlier, it's sometimes called the energy as well. That's why I have E here, but you can keep it as L, L as well, right? So that's your loss. And so this partial derivative is the gradient. So that's the direction of the descent, right? The steepest descent. And then the lambda, it's called the learning rate. It just tells you how big a step you take, right? Do you take big steps? In that case, lambda will be high, just a real number. It could be like 0.1 or something, just a real number. Or do you want to take very big step, like 0.1, maybe like a step like this, and then 0.01 means you are taking steps very carefully. That means you are taking like only very small steps at a time, right? So that's what lambda means. And the next location, so the next location, your next location, that means after you take the step, you will end up with that new location, right? So I hope this is clear now. This was your where you start with, and this is the direction of your movement, right? This is the direction of your movement, and lambda is the magnitude of your step. And so after doing all this, what you have is your new location, right? Your next step. And then from there, you keep on doing this. You keep on doing this again and again until you end up in the bottom. So this algorithm won the Nobel Prize. It's very simple, right? We could have invented it, but I guess we are a bit too late now. Jeff Hinton already won the Nobel Prize for this algorithm, the whole thing, backpropagation and stochastic gradient descent. So it's just this. Let me just explain it with pseudocode for people who are who are familiar with Python code. This is not exactly Python, but it's just pseudocode. So you have to start somewhere, right? So you are starting the journey somewhere. It doesn't really matter where you start from. So that's why so sometimes you will start like random initialization. So you can start from anywhere really. But if you keep applying this algorithm, you will end up where you want to end up with, right? So yeah, so you randomly initialize it, and then you take a little bit of your data set. So that's why you can work with multiple, like very large data set, because you are not consuming the whole data set. You are only consuming a small part of it at a time. So it will fit onto your GPU or your laptop or whatever, right? So that's why this algorithm is really, really scalable. And then you take your step, uh, the model forward pass, and then you calculate your gradient, which was that term, this term, and then you take the step. So this was the equation, the full equation, this equation, right? Yeah. So it's very simple. Actually, if you write this code in PyTorch or TensorFlow or JAX, your actual Python code will be very similar to this pseudocode I have here. So it's super simple, easy to understand. Of course, it's a bit difficult to master, but it's not that difficult to understand at all. Okay, so that's how it works. Now let me talk a bit about applications of GenAI. Um, so one application is LLM chatbots, as you have all used. But sometimes these chatbots they can go wrong. You have to be aware of that too. For example, this is something I asked from ChatGPT when it was initially released. So being the egoistic person I am, the first question I asked from ChatGPT was, "Who's Sadeep Jayasumana?" I wanted to see whether it knows me. So this was back in 2023 or something when I took the screenshot, and then it went on something like this. Sadeep Jayasumana is a Sri Lankan software engineer known for his contributions in the field of computer science. It's all go good. Okay. But then it starts suddenly saying he gained significant attention for his work on Deep Nude, an AI-powered software that generated realistic nude images of women using deep learning algorithms. However, Deep Nude sparked controversy and ethical concerns regarding privacy and consent, leading its removal from the internet. Please don't drop out from the seminar. This is not true at all. I have nothing to do whatsoever with anything called Deep Nude or anything remotely connected to that. It's just complete hallucination. So after this, it's completely hallucinating about me. So that's like an ugly part of these LLMs that you have to be careful about um, when we are working with these things. And so I thought this problem would be fixed with Gemini. But when Gemini was initially released, it was called Bard back then. I asked the same question, and then it says, who's Sadeep Jayasumana? And it said there's no widely known, no significant person named Sadeep Jayasumana. So I was really confused, like what's worse, calling me insignificant or calling me a pervert? I guess both are equally disappointing. But they have come a long way. Like if you ask this question now, now they do something called retrieval augmented generation or RAG, and then they go on and search on the internet and then they summarize it. So LLMs have gotten much better now in 2025. Okay, so the field is progressing very fast. The second one, image and video generation. So this was something I did a lot when I was at Google. So actually my last few projects were entirely based on image generation with transformer models. So again, it's very similar to what we discussed. It's a transformer model. I mean, there are various ways of doing image generation, but here I'm talking about image generation with transformer models. It's very similar to the next token or next word prediction. So you just give it a prompt, and then it will keep on predicting the next word. But the only difference is here the words will not be English. Instead, they will be image patches, right? But the idea is similar. You still have a dictionary, you still have an embedding table and all that. And it will predict image patches. And then you put those patches together and then you have an image, right? So it's exactly the same thing. Next token prediction task, right? Next token prediction task. So the underlying backbone is the same. You still have self-attention, you still have transformers, and you still train them the way I was describing using cross entropy and gradient descent. Okay, so another application. So this is also something, one of my first projects at Google. I worked on Google YouTube ad optimization. Or another example would be YouTube recommendation. For example, when you watch a lot of videos, Google recommends you videos on the right hand side. So I won't show you my YouTube interface right now because then you will know all sort of what sort of weird things I'm into. But as an example, like hypothetical example, let's say I watch a lot of Sri Lankan videos and also I watch like food related videos, recipes sort of thing, then the transform model will know that I'm Sri Lankan and it will also know that I'm interested in food and maybe it will predict like a Sri Lankan recipe, right? And in order to do this, transform model has to understand various things that I'm Sri Lankan and I'm interested in food and all that. So again, the self-attention mechanism is the mechanism behind the scenes. So that mechanism, the interaction we were talking about, like the speed dating scenario where every vector talks to each other with n-squared connections. So that's the mechanism behind this sort of models as well. So these recommendations, by the way, that's like the cash cow in Silicon Valley. So all the big tech companies make like real money with recommendation systems. Although in academia, these like less highlighted less often. For example, like Amazon, they have this, what you would be interested in next, Google ads, YouTube ads, Facebook ads, all those things are Netflix, they predict what movie you would be interested in. TikTok, it predicts what video you would be interested in next. YouTube Shorts, Facebook Reels, all these things. They heavily rely on this sort of recommendation systems, which are very often implemented with transformer models, the models we discussed today. So previously, like all this, there were some things like I even forget the names, matrix factorization. Those are very old techniques now. In the modern tech world, those are getting replaced with these Gen AI transformer style models. Okay, so that's pretty much it for the content, the technical parts. But I want to finish with how to get it to the field, because that's the question I frequently get from university students and early career researchers. So there are few things that you need to specialize if you are really serious about data science or AI. Like the OCTAVE also, we do a lot of data science AI sort of thing. So these are the key the competencies or skills we look for as well. And at Google also, when we hired Gen AI or AI researchers, these are the skills we expect from them. So I've done a lot of interviews at Google as well, where we focus very heavily on statistics and probability theory, especially for research scientist roles in AI and machine learning. So you have to be strong in statistics, your probability, understanding Bayes theorem, and understanding joint probabilities, marginal distributions, Gaussian distributions, and all sort of things. And then the linear algebra. So I talked about vectors today briefly, but it goes a bit deeper than that. Do you understand matrix multiplication? I mean, it's very simple stuff, yeah, but a solid foundation is required in that area as well. And then calculus. We talked about the steeper descent and gradient descent algorithm, and taking derivatives a little bit today. But yeah, so that sort of calculus. If you are really serious about doing research in AI, that's also something you need to focus on. And last but not least is your programming skills. In particular, your programming skills with Python. I mean, places like Google, they don't really test you on a particular programming language. They are more interested in your uh, skills in data structures and algorithms. But Python programming with Python would also be a good skill to have. So here are some resources. I'll give you a minute to uh, note this down. I like quickly grab my water bottle. Okay. Yeah, probability and statistics. So it's never too late to learn probability and statistics. I mean, I was also not very keen on probability and statistics early days. Um, I mean, a lot of mathematicians, they also don't like probability and statistics that much, but it's like a really interesting topic once you get into it. And it's a must if you're serious about data science, machine learning, AI. Probability and statistics background is a must, because that's the day-to-day language we speak in machine learning research. And linear algebra again, there are some resources. So probability and statistics, by the way, so this one is a quite fun book. It's a very old book, but it has these fun brain teaser kind of questions in probability and statistics. And the second one is more like a formal textbook. Um, and this Gilbert Strang, he's very old now. He retired recently, but it's like there's a fun lecture series on YouTube on linear algebra where he talks about like XCD decomposition, eigenvalues and all sort of things. So it's important to have that background as well. Calculus, again, like I don't have a specific reference here because you don't need to go to that that deep into calculus. And yeah, Python programming. So this is like an interview specific book. It was originally written for interview practice for companies like Facebook, Google, Apple, Amazon, that sort of companies. But yeah, but still it has nice tips on Python programming as well. Okay, cool. So that's the end of the presentation. Thank you very much for attending.
And that brings us to the end of this webinar recording. Thank you for watching, and don't forget to leave your feedback in the feedback form link in the description below.